Okay, guys, so here we are in the IS number 17 notes, and the big ideas and check your understanding. So I've gone ahead and written out the big ideas. I'm just going to go over them real quick. Learning target number 1 is about the conditions. These are the same as the conditions for confidence intervals for means, right? The means do not change conditions. So you have to have a random sample, you have to meet the 10% condition that N is less than 1/10 of your population, and then you need to meet the condition to have a normal sampling distribution. There are 3 ways to do that, remember. Either the population is said to be normal, your sample size is greater than or equal to 30, so the central limit theorem applies, or you check the sample distribution and there's no strong skew or outliers. This is the condition we had to go with on the front side. We'll see one of the others in the check your understanding problem. Learning target number 2 is about being able to calculate the test statistic for means. So remember, we don't know the population standard deviation. So we have to estimate it with S, the sample standard deviation, which means instead of calculating a true z-score, we're actually calculating this t-value. The test statistic is a t-value. So it's the statistic, x bar, minus the parameter mu, divided by the standard error, S, divided by the square root of n. Okay, so then that t-distribution looks pretty much like a normal curve, but we label it with t and then whatever the degrees of freedom are in parentheses. We still put mu in the middle and then add the standard error, 3 up and 3 down. Okay, learning target number 3 is about finding the p-value. And again, this is different than than what we've done before. This is new. So we can use table A3 with your degrees of freedom and your test statistic to find the area in one tail, but that's really unwieldy and it just gives you a range of values. So I strongly suggest that you use the TCDF function, enter your lower and upper bounds for your t-value and then your degrees of freedom, and that will give you your p-value. Okay, so let's do the check your understanding problem. It says the level of dissolved oxygen, which they're going to label DO, in a stream or river is an important indicator of the water's ability to support aquatic life. So a researcher measures the DO level at 30 randomly chosen locations. I'm instantly thinking, oh good, it's a random sample along a stream. So here are the results in milligrams per liter. There's X bar equals 5.27 and the standard deviation is 0.939. And then it says an average dissolved oxygen level at or below 5 milligrams per liter puts aquatic life at risk. Okay, let's get that right. Average dissolved oxygen, so DO level at or below 5 milligrams puts aquatic life at risk. So do the data provide convincing evidence at alpha equals 0.05 significance level that aquatic life in this stream is not at risk or that it's safe? They put not in there, not at risk. So it's at risk if the level is, the average level, I should say, is at or below 5 milligrams. But to be not at risk would be the opposite of that. So the opposite of at or below would be above or greater than 5. Okay, that's going to be important when we try to write out our hypotheses here in a second. So let's go ahead and write down the parameter and statistic. Obviously, it says average, so we're looking for a mean. So our parameter is going to be mu is equal to the true mean. It's a dissolved oxygen level. I'm going to abbreviate that DO. True mean DO level. Okay, the statistic they've given us is the sample mean, X bar, which is 5.27, and it says it's in milligrams per liter. Okay, so then my hypotheses, my null hypothesis and my alternative hypothesis. So I'm trying to see if I have a convincing evidence that it's not at risk or that the mean is greater than 5. The average is greater than 5. Right, it's at risk if the mean is at or below 5 milligrams. So let's see, the highest we could be and still be at risk would be exactly equal to 5. So we're going to say mu is equal to 5, and then we're not at risk if we're greater than 5. That's what we're going to prove, so that's what we're choosing. If the question had asked the opposite thing, if it had said, do the data provide convincing evidence that the stream is at risk, that's when we would make mu less than 5. But since we're trying to see if it's not at risk, we're making mu greater than 5. Okay, and then my significance level is 0.05. Okay, I think I've stated everything I needed. Notice on the front side, we stated all of those same things as well. We had our hypotheses, what the parameter means, our significance level, and the sample mean. Okay, we just had some guiding questions. Now we're gonna have to know, that's what we have to state. The name of the procedure, this is also new, so I guess I'll write it in a different color. This is called a one sample t-test for mu. Notice we've only done one sample thing so far. So all of our names has started with one sample. And then this is for means, so I have to use the t-distribution. So it's a t-test for mu. We had a one sample t-interval for mu as well. That was the confidence interval. The last thing we did was that one sample z-test for proportions. But again, z goes with proportions, t goes with means. Okay, so then we have to check our conditions. The first one is whether or not we have a random sample. And it does say that we have 30 randomly chosen locations. So I know you guys are probably getting kind of tired of writing out these conditions, but the conditions are really, really, really important to making sure our results are valid. So I do expect you to write this entire 4-step process out on every homework problem. Now, that means I probably won't give you that many homework problems, but I do expect you to write all this out. So number 2, the second condition is the 10% condition. We have n equal to 30. So is 30 less than 1/10 of all the population? Let's see, the population would be stream locations. Yes, I think in a given stream you can find way more than, let's see, 10 times 30 is 300, way more than 300 stream locations. So both of those conditions are met. And then the third condition is to see if our sampling distribution fits a normal model. So let's see, we don't know anything about the population distribution, but we do know that our n equal to 30 is greater than or equal to 30. So the central limit theorem applies. Good, that condition is met. We don't actually have the sample data here, so it'd be really hard for us to sketch it and see if there's a strong skew, so I'm glad that our sample size was big enough. Okay, so now we get to our do step. And again, this looks exactly like it did for confidence intervals. It's just the stuff that we do is a little bit different. Our general formula is now for the test statistic. So my test statistic is equal to my statistic minus my parameter divided by the standard deviation. And then I'm going to write the specific formula. It was a z-score for proportions, but for means it's a t-value. So my statistic is x bar minus my mean, which is mu, divided by my standard deviation or standard error of s divided by the square root of n. Okay, so before I plug all that in, I actually want to go ahead and start sketching my picture. So let's see. My normal curves have not been very symmetric lately, but that's all right. Okay, I'm going to put my mean at the middle. That's what I am hypothesizing my mean to be, 5. Now, in order to sketch the rest of my picture, I need to know what this s divided by the square root of n is actually equal to. So I'm just going to kind of write it up here out to the side. S divided by the square root of n. My s is given in the problem. It says 0.939 divided by my square root of n, which is the square root of 30. Okay, let's calculate that. 0.939 divided by second square root of 30. So my standard error is 0.171. 0.171. Okay, so that's what I'm going to add and subtract to 5. So it'll be 5.171, right? I can add it just fine. I'm going to go ahead and use my calculator here to get the rest. 5 plus 0.171. That was my original one, so plus 0.171 and plus 0.171. Okay, so 5.342. And then 5.513. I can go in the opposite direction as well. And I will when I actually post these notes on Schoology. But for now, I'm going to leave it be because I know that my actual sample mean was 5.27. So I know I'm only going to have to go above the mean for what I'm interested in. So before I do that, though, I do want to label this curve. It is a t-distribution with a degrees of freedom of 29, right? 30 minus 1 gives me 29. Okay, so my sample mean of 5.27, I can tell is going to fall between 5.17 and 5.34. It's going to be a little bit closer to 5.34, and then I'm going to shade that. So I guess I'll shade it with my red. Okay, so that is going to be my probability that my sample mean X bar is greater than this time, right? I want to be as extreme as the sample results or more. So greater than or equal to 5.27. Okay, so now that I know what that probability is that I'm looking for, I'm gonna go ahead and find the test statistic that will help me find that area. So let's plug in. I have X bar is 5.27. The mean is 5 from my hypothesis. The sample standard deviation is at 0.939 divided by the square root of 30. Now, I do know that this value is I already know that it's 0.171, but if you remember, there were other digits after that, right? So I'd be rounding if I just put 0.171. I don't want to round, so I'm gonna retype that whole thing into my calculator. And I'm putting little parentheses around there to help me remember to do that in my calculator. So I have parentheses 5.27 minus 5 end parentheses, and then divided by new parentheses 0.939 divided by the second square root of 30. I have to remember to arrow out from underneath the the square root and then end my parentheses. All right, so I'm going to round to 3 decimal places. Again, I get 1.575, it looks like. So this gives me 1.575. It prompts me to write my test statistic over here. You're not going to have this layout given to you, so you can write it wherever you want, but I'll go ahead and make it really clear. T is 1.575. Okay, so if we were going to use the table to find our p-value, we would need the degrees of freedom, 29, and then find where 1.575 fits into that row. So degrees of freedom of 29, looking for 1.575. Okay, 1.575 is going to be between these two values, 1.699 and 1.311. So I'm going to go up and find the area on one tail. It's going to be between 0.05 and 0.10. So I know from table A3 that I'm going to be between 0.05 and 0.10, but that's not very specific. So I am going to go ahead and use that TCDF function to find my p-value. TCDF, let's see. This time my lower is the actual t-value I got. Where'd it go? 1.575. And then I go on forever in the positive direction. So I'm going up to like 10,000 maybe. And then my degrees of freedom that it's going to ask for are 29. Okay, so let's enter that. Again, I go to second distribution to get to TCDF. Hit enter. My lower, again, is 1.575. My upper is something like 10,000. Degrees of freedom are not 9, but 29. And paste, enter one more time. 0.063. Okay, so table A3 was correct. My p-value is between 0.05 and 0.1. It's 0.063. But this, again, is way more specific. I like this better. Okay, so let's conclude now. We always started out with since our p-value, and then state what the p-value is equal to, 0.063. And then we compare that to the significance level. So remember, the significance level it told us was 0.05. So 0.063 is greater than alpha, equal to 0.05. And like we wrote on the previous page, if our p-value is greater than alpha, then we fail to reject the null. So that is what we're going to do here. We fail to reject the null. If we fail, it means we do not have enough evidence. So that's what we say next. We do not have convincing evidence that, and then we state our parameter. So what was the parameter again? The true mean DO level, or dissolved oxygen level, so that the true mean DO level in this stream is, what was our alternative? Is greater than 5. Greater than 5 milligrams per liter. Okay, but that still doesn't really answer the question, right? That was the specific dissolved oxygen level, but the question specifically was whether or not the stream is at risk. So we do not have we do not have convincing evidence that the true mean DO level in the stream is greater than 5 milligrams per liter, or that the stream is not at risk. We do not have convincing evidence of that. We don't have convincing evidence that this stream is safe. It could be safe, we just don't have enough evidence to say that for sure. Okay, guys, so that is it for hypothesis tests for means. Make sure that you do that homework with the 4-step process every time. State, plan, do, conclude. Include all of these things that are stated. Okay? All right, let me know if you have any questions.